And we'll get rid of that. And that. Okay, so for today, we're doing a summary here of the physical chemical properties of elements within a group. So yesterday, we started by talking about Bohr-Lewis diagrams, and I hope that from that lesson, we realize that elements within a group, up and down, have similar properties when it comes to their outer electrons. And then yesterday, we did an experiment where you got to observe the physical properties of some of those elements within a group, and then you got to observe the chemical properties of them when we reacted them with water. And I'm hoping that you, when you finish your lab, come to the conclusion that elements within the same group have similar chemical and physical properties, all right? And the reason behind that has everything to do with their outer electrons. How many outer electrons, or how many dots, do the elements in group 1 have? If we're drawing a Lewis diagram, how many outer electrons or dots? Isaac? 1. Group 2? 2. Now, we're not dealing with these guys. Group 13 or 3? 3, 4, 5, 6, 7, 8. So it's the fact that they've got the same number of outer electrons that gives them their similar properties. Okay, let's keep rolling here. And I'm just going to bring the whole thing up, and you can write this down. This is simply a statement of what I've just stated. Those of you who need to go to the amphitheater, 3 minutes should be plenty of time to get you there. You could probably even get lost once with 3 minutes worth. You may proceed. You can go ahead. Don't bump my cart. You can come in behind me here, because I've got it oriented in this pink. Okay, so let's please write this down. Let's please get this information. They have similar physical and chemical properties. It means they look the same. They react very similarly. They even form compounds with the same chemical formula. So that's a little bit of a look ahead to the next part of this unit. The next part of this unit, we're going to be looking at what happens when they make some chemical formulas, make some chemical compounds. On my next slide, we're going to take a little preview of that. And why do they have these similarities? Because elements within the same group have the same number of valence electrons. What did valence stand for? I use the term valence a couple times. Outermost shell. Very good. The outer electrons. They're the ones that get involved in chemical reactions. Yesterday, when you put that sodium in the water and it reacted vigorously, I think it's the hydrogen in the water that is ripping the electrons off of the sodium atoms. It's giving up its valence electrons. We have various devices out there. Are we good to go? We good to go? Again, I don't know. People are writing on phones and various things. It's hard to keep up with you guys. So let's just do a little review of some Lewis diagrams. We'll do this one at a time together. Don't feel you've got to write this all down at the same time. So let's do a little review of some Lewis diagrams here. Magnesium. You've got a table here, or perhaps you've got your table. How many dots am I putting around that magnesium? How many dots am I putting around the magnesium? Felicia's distracted by something exciting on this other side of the room. What are you distracted by? My nice chart paper? Oh, okay. Well, Felicia, magnesium right there. How many dots am I putting around it? 2. Nice. I'm not putting them together. 1, 2, because it's not helium. How many dots go around oxygen? Dots around oxygen. Conrad? 6. 1, 2, 3, 4, 5. Whoops. 5, 6. Right? 2, 2, and 1, and 1. And in the next unit, we're going to see that that's a nice match, that the magnesium can give up its 2 and the oxygen can take its 2. That's going to result in a chemical compound that has a formula of MgO. All right, now I'm not going to draw the dots in. I'm not going to draw the dots being traded yet, but I'm hoping that you can see that if this electron is given here to that spot, and this electron is given here to that spot, that those two things fit together nice and perfectly to form a compound with the formula of MgO. All right? So if we look at calcium, you'll notice calcium is also in group 2, just down below, just like we saw in the reaction yesterday. Again, it has 2 dots. And oxygen still has its 6 dots. And you'll notice that with that nice pairing, we can also make them fit together very nicely. So again, we can have this guy go with this guy go with this guy. And so calcium, just like magnesium, can form a compound with the same formula because it has the same properties. CaO. All right? How many dots does aluminum have? Yep. 3. 1, 2, 3. Chlorine. How many dots in chlorine? Yep. 7. 1, 2, 3, 4, 5, 6, 7. All right? So, if aluminum is going to give its electron to chlorine, that chlorine is now full. How many chlorines am I going to need to satisfy that aluminum in order to take care of this? Aluminum could only get rid of 1. Chlorine is now full. How many chlorines am I going to need? Yep. 6 chlorines. If I have a second chlorine here, let's take a look. Let's draw this second chlorine. And this electron here is going to go over into this spot. All right? So now I've taken care of 2 of their electrons. I just need 1 more. And this electron can then go to that spot and pair it up. And 3 chlorines will take care of that aluminum. So it will end up with a compound of AlCl3. We will do more of this in more detail in the next unit. But what I'm saying is, if they're in the same family, then they'll behave similarly. How many dots around boron? Yep. 3. 1, 2, 3. How many dots around fluorine? Yep. 7. 1, 2, 3, 4, 5, 6, 7. Notice how it's just like the aluminum and the chlorine. So what formula would it make? How many fluorines are going to be needed? What's that formula going to be? Brianne, what do you think? I would need 2 more fluorines, but if I were to jump straight to the formula, what would my formula be? What's my first one going to be? B, and then F, and how many? 3. So you'll notice the formula looks the same because they've got the same electron properties, which allows them to bond in the same way. So that's what we're saying. Chemicals in the same family will create compounds that are the same, no matter whether it's up or down. The formulas will be the same for those compounds, all right? Because they're in the same families. All right. Yesterday, we did an investigation on the reactivities of the metals. I'll put the examples in. We'll answer those in a moment. Which one of our elements reacted the best? What was the fun one? Potassium. And you put in, pow! It's just like, the way it went. It's awesome. very reactive. Metals are more reactive when you go down a group. Potassium was more reactive than sodium. It has everything to do with the large atoms. Because there's an extra orbit, the atoms are bigger, the reaction is more vigorous. Does anybody remember how the calcium was? It was those little beads. Was it exciting? No, it just kind of bubbled a little bit. Made it purple. It's a neat little reaction, but it's, sorry, pink, fuchsia. I don't even know what fuchsia is. Somebody told me that once. It's fuchsia, Mr. Sanders. I'm like, what's a fuchsia? Anyway. If we compare beside each other, and I don't know if we did that yet, but you're going to have to probably answer that in your lab as you get to work. Potassium reacted like very vigorously, and calcium did not react that much at all. We could even compare sodium to magnesium. Sodium danced around there. That was kind of a neat little reaction as well. But magnesium, if you didn't have hot enough water and you didn't leave it long enough, you didn't even see the little bit of pink. Did anybody see the little bit of pink around the little pieces of magnesium? That's cool that you did it. It's so slow. Magnesium is such a slow reaction that you'd have to leave it there for a couple of days and it might slowly turn a little pink. So again, as you move right, it becomes less reactive. As you move down, it's more reactive. Right here, I've got a link to a YouTube video that shows the reactivities of these metals. It even goes all the way down to rubidium. I can't show the YouTube video and simultaneously record my voice, so we will come back at the end of the note and we'll watch the videos that show that. Okay? Well, francium is a radioactive unstable product of an element that's heavier than it. It might be radium, or it might be, I got to go back to, it's probably thorium, right? So when thorium breaks down, I think it makes francium, I'm not sure. So it doesn't, you can't gather up a lot of francium because there's not a lot of it that exists in nature. Cesium, you saw the potassium, that little piece, same thing. Cesium, like faster. Would it be like a bomb? Not necessarily. It's just very fast, right? If you had a lot of it, if you had a lot of potassium, it'd be dangerous because it would go fast. This would go even faster. Yeah. Okay, so which metal is more reactive? Magnesium or aluminum? Which metal is more reactive? Magnesium or aluminum? Conrad?
I'm going to go magnesium.
Yeah, and why is that?
Well, magnesium more to the left, aluminum.
Exactly, perfect. Elements on the left are more reactive, elements on the right are less reactive. So magnesium is more reactive, okay? All right? Why? Because it's to the left. There is a reason behind it. In the grade 11 university, we go into great detail on how to explain why that is. So Jenna can tell you what the answer is to that. Which is less reactive, copper or silver? Now notice we're choosing some transition metals, but we can still make the same thing. Which is less reactive, copper or silver? Yep, Conrad.
Copper is higher.
Yeah, copper is less reactive. It's higher on the scale. Which is less reactive, copper, because it's higher up on the periodic table. All right. Okay. Let's talk a little bit about nonmetals. We didn't do that yet, so we'll just talk briefly about that, and then we're done. So we've talked about metals and the way they behave. Let's now talk about the nonmetals and the way they behave. Well, it turns out that the property that governs the reactivity of nonmetals is exactly opposite to the property that governs the reactivity of the metals. So whatever we've said about the about the metals, it's opposite for the nonmetals. I've then left a blank. If we're looking for the reactivity as we move down the group. Let's say we're talking about the halogens, and we're moving down the group. Are they becoming more or less reactive if it's the opposite of a metal? It's becoming less. The nonmetals actually get less reactive as we move down. They're the opposite. So nonmetals are less reactive as we move down a group. So if you run into some iodine, you can put that on your cut, maybe a little bit of iodine to sterilize the cut, but you definitely don't want to put any fluorine on there because it would burn a hole through your hand. You don't want to do that because it's very reactive. Chlorine is a very vigorous chemical. You can get it in bleach in a certain form, and when you're dealing with pure bleach, you want to wear safety goggles and gloves. To be honest, I don't at home when I put bleach into the washing machine, but I should. At one point in time, I remember I was pouring the bleach into the little bleach spot that goes in the washing machine, and a drop came and it landed right at below my eye, and I went, just missed. Because you probably know what it would be like if you had if you get anything in your eye, but if you've ever had salt water in your eye, it's really aggravating. I'm glad that little drop of bleach didn't land right in my eye. It would be really quite painful, I would think, right? Okay, nonmetals are blank reactive across the period. So if we're going this way, across the period to the right, what's going to happen to the reactivity as we go this way for nonmetals? Keeping in mind it's opposite. It becomes more reactive. It becomes more reactive. Excellent. Not including the noble gases. These, the reactivity stops because their shell is full. And again, we'll talk about that more later on. Okay? So if we're looking at the metals, well, which one would be the most reactive metal? The most reactive metal. I'm not talking about the nonmetals right now. I went back to the metals just to mess with you. Where is the most reactive metal on our table over here on the metal side? Yep. It'd be in the first column, correct. And now at the top or the bottom? The bottom of the first column, which is why the question was asked about francium. That is the most reactive metal. Which would be the most reactive non-metal? Where would the most reactive non-metal be? Very reactive, very dangerous. Most reactive non-metal. Again, it is opposite, right? So what's it going to be? Jess, what do you think? At the top and to the right, but not including these guys. So fluorine is the most reactive non-metal. All right? Excellent. So which non-metal is more reactive? Oxygen or fluorine? Fluorine. Fluorine is the most reactive. It's the furthest to the right. Which is the most, which non-metal is less reactive? Chlorine or bromine? Which is less reactive? Bromine. It's near the bottom. Bromine. It's near the bottom. You've heard of, if you've got a hot tub or a swimming pool, you can put chlorine in it, right, to keep it clean. You can also get a version of it which is bromine, like it's the chemical equivalent of the chemical they use that has chlorine in it, except bromine, and they say that it's easier on the skin, right? Bromine is less reactive. Which of the nonmetals is the most reactive? Chlorine or argon? Chlorine or argon? What do you think?
Chlorine, argon.
Yeah, so it doesn't react. That's a little bit of a trick question. Chlorine is most reactive, even though it is to the left. The noble gases don't count. I've got another video there to show. As soon as I'm done recording, I'll go back and show those videos. Okay. So there's the Unit 1 review, and I'm going to show you where that is. You don't even need to write down that. I'm just going to show you what the unit the review is. And so I am done that note, so you can get ready to work on labs or on various things. But I am going to reopen the note in a moment to show you those,
We'll do